Welcome to my comprehensive guide on API security with a focus on the OWASP Top 10 API security risks for 2023, which currently still applies to 2024. Today, we'll explore key measures for ensuring robust API security in today's digital world and showing hands-on examples. Let's begin by understanding what OWASP is. The Open Web Application Security Project, or OWASP, is a nonprofit organization focused on enhancing software security. Founded on December 1st, 2001, OWASP is renowned for its top 10 lists and various open source tools that help organizations bolster their security measures. The OWASP API Security Top 10 is a specialized list that highlights the most critical security risks for APIs. This list, first released in December 2019, provides essential guidelines for securing APIs against common threats. I will explain each risk from the list in more detail during this course. APIs have become pivotal in facilitating seamless data exchange, which is crucial in today's digital interactions. Companies leverage APIs to incorporate functionalities such as mapping, payment processing, and user authentication, thus saving significant development time and resources. Despite their advantages, APIs introduce unique security challenges that traditional tools often can't address. Many organizations struggle to defend against API-specific vulnerabilities, resulting in a rise in data breaches and security incidents. The swift adoption of APIs has exposed new attack vectors. Attackers can exploit insecure APIs to bypass conventional security measures, gaining direct access to sensitive data. This makes securing APIs a critical priority. The 2023 OWASP Top 10 API Security Risks provides updated guidelines to tackle evolving API security threats. By adhering to these recommendations, organizations can significantly enhance their API security and protect against a wide array of vulnerabilities. The OWASP API Security Project has become an invaluable resource for the global security community. It is widely recognized for its efforts in raising awareness and providing practical solutions for API security. APIs are integral to modern applications, making their security crucial for protecting sensitive data. Ensuring robust API security is essential not only for preventing data breaches, but also for maintaining user trust and safeguarding the integrity of services. In conclusion, the OWASP Top 10 API Security List is a critical resource for addressing API security. Organizations must prioritize API security to protect against emerging threats and ensure the reliability of their digital services. Now, let me explain each risk from this list. Let's talk about the first risk listed, which is Broken Object Level Authorization, commonly known as BOLA. Today, we will uncover the nature of this critical vulnerability and explore strategies to protect against it. BOLA, or Broken Object Level Authorization, is a vulnerability that occurs when APIs do not enforce proper authorization controls. This flaw enables attackers to access data belonging to other users, which should be restricted. Attackers can exploit BOLA vulnerabilities by modifying object identifiers in API requests. These identifiers, whether sequential numbers, UUIDs, or generic strings, can often be found in URLs, headers, or payloads, making them easy targets for manipulation. BOLA vulnerabilities often stem from inconsistent or missing authorization checks. Even when a robust authorization infrastructure exists, developers might forget to implement these checks, leaving the application vulnerable to exploitation. The consequences of BOLA can be severe. Unauthorized access can lead to data breaches, manipulation of data, or even full account takeovers. Such incidents pose significant risks to both users and organizations, potentially leading to substantial financial and reputational damage. To understand BOLA better, let's look at a real-world example. Imagine a user making an API request to access their profile data. If altering the user ID in the request allows them to view another user's profile, it signifies a BOLA vulnerability. For instance, if a request to the URL shown on the slide returns one user's data and changing the user ID to 202 shows another user's data, the API has a BOLA issue. Identifying BOLA vulnerabilities requires testing by altering object IDs in API requests. If modifying an ID allows access to another user's data, it confirms the presence of a BOLA vulnerability. This can be tested by substituting different object IDs in various request types and verifying if unauthorized data is retrieved. Here's an example to illustrate how BOLA can be exploited. Consider an API request to access user profile data. If a user with the ID 101 sends a request and gets their details, but then changes the ID to 202 and retrieves another user's data, it indicates a BOLA issue. Let's look at the sample code. In this example, we see that user 101, John Doe, accesses his data through the API. However, if John changes the user ID to 202 and retrieves Jane Smith's data, it shows that the API is vulnerable to BOLA. This occurs because the API fails to properly authorize the request to ensure John can only access his data. BOLA can manifest in various ways based on how API resources are structured. Resources might be managed by individual users, groups, or a combination. Ensuring proper access controls for each structure is crucial to prevent unauthorized access. To prevent BOLA vulnerabilities, it's vital to implement robust authorization checks based on user roles and permissions. Using unpredictable resource IDs makes it harder for attackers to guess them. Regularly testing your authorization controls can ensure they are effective and up to date. Best practices to mitigate BOLA include using comprehensive authorization mechanisms tailored to your user policies. Employ GUIDs for resource IDs to make them less predictable. Write and maintain thorough tests for your authorization mechanisms to ensure they function correctly before deploying any changes. All right, time to explain the next API security risk from the list. Time to speak about broken authentication, which is second on the list. We'll explore this critical vulnerability and how to strengthen your API's authentication mechanisms. Broken authentication refers to weaknesses in the API authentication process. All APIs that handle sensitive information must have robust mechanisms to verify user identity, ensuring that entities are who they claim to be. This process often involves usernames, passwords, tokens, and multi-factor authentication. Authentication mechanisms are prime targets for attackers since they are exposed to everyone. Although exploiting these mechanisms may sometimes require advanced skills, the availability of exploitation tools makes these attacks easier and more feasible. Authentication issues are prevalent due to misconceptions about the boundaries and inherent complexity of these systems. Fortunately, there are straightforward methods for detecting broken authentication, making it easier to identify and address these vulnerabilities. The consequences of broken authentication can be severe. Attackers can take over user accounts, access personal data, and perform sensitive actions on behalf of users. This makes it difficult for systems to differentiate between legitimate user actions and those of attackers. One common issue in broken authentication is weak password policies. These policies fail to protect user accounts effectively by allowing simple passwords, enabling brute force attacks, and permitting password changes without confirmation. Ensuring strong password policies is critical for securing user accounts. Credential stuffing is a type of attack where attackers use stolen username and password combinations from data breaches to gain unauthorized access. This method allows attackers to attempt numerous login combinations rapidly, often succeeding in compromising accounts. Predictable tokens are generated through weak processes, making them susceptible to attacks. If tokens are easy to guess, deduce, or calculate, attackers can use them to gain unauthorized access to the API. Misconfigured JSON Web Tokens, or JWTs, can introduce several security risks. Issues like accepting unsigned tokens, not checking token expiration, and using weak signing keys can compromise API security. It's essential to configure JWTs correctly to ensure robust authentication and authorization. Let's consider an example of broken authentication. Imagine a system that allows users to create simple passwords and doesn't enforce multi-factor authentication. An attacker can use credential stuffing to try numerous password combinations. Additionally, if the system uses predictable tokens, the attacker can easily generate valid tokens and gain access to user accounts. In this example, the system allows simple passwords like password and admin123. The tokens 123456 and ABCDEF are also easy to guess. Such weak security measures make it easy for attackers to exploit the authentication process and gain unauthorized access. To prevent broken authentication, implement strong authentication mechanisms based on industry standards. Incorporate multi-factor authentication and anti-brute force mechanisms to enhance security. Regularly test and audit your authentication processes to identify and fix vulnerabilities. Time to move on to the next risk from the list. Let's talk about broken object property level authorization, or BOPLA, which is number 3 on the list. We will dive into this critical vulnerability and discuss how to prevent it. BOPLA, or Broken Object Property Level Authorization, is a vulnerability that combines two issues: excessive data exposure and mass assignment. Excessive data exposure happens when an API provides more data than necessary in a response. Mass assignment occurs when user input can modify sensitive object properties without proper authorization. Excessive data exposure happens when an API responds with an entire data object instead of just the necessary data. This can lead to the exposure of sensitive information. API providers should always filter responses to ensure only the required data is included. Consider a scenario where a user requests their profile information. Instead of just receiving their name, they also get their date of birth, email, and phone number. This is an example of excessive data exposure, where more information than necessary is provided. Mass assignment occurs when user input can modify sensitive object properties without proper checks. Users can include unauthorized parameters in their requests, which the API accepts and processes, leading to potential security breaches. Imagine a user creating an account. They include an additional parameter, is admin, in their request to gain administrative privileges. If the API does not sanitize this input, the user could successfully create an admin account. Let's look at a sample request. In this example, the user adds the isAdmin parameter to their request. If the API does not properly validate the input, the user could become an admin, leading to a significant security risk. To identify BOPLA vulnerabilities, inspect API responses for excessive data exposure. Test for mass assignment by adding unauthorized parameters to requests and checking if the API accepts and processes them. The impacts of BOPLA can be severe. Unauthorized access to sensitive data and modification of object properties can lead to data breaches, privilege escalation, and even account takeovers. It's crucial to address these vulnerabilities to protect your API. To prevent BOPLA, implement strict authorization checks for object properties and filter API responses to include only the necessary data. Avoid using generic methods that automatically bind input to object properties. Instead, carefully select which properties to expose. Onwards to the next risk from the list. Time to speak about unrestricted resource consumption, which is number 4 on the list. Today we'll explore this significant vulnerability and discuss how to protect your APIs from excessive resource use. Unrestricted resource consumption happens when an API does not have adequate safeguards to prevent excessive use. This vulnerability can lead to a denial of service and result in increased operational costs due to resource overuse. Attackers can exploit resource consumption vulnerabilities through simple API requests that generate high traffic loads. These attacks can be executed using multiple concurrent requests from a single computer or leveraging cloud computing resources. Many APIs lack proper limits on client interactions and resource consumption. Attackers can craft API requests that include parameters to control the number of resources returned, revealing weaknesses through response status, time, and length analysis. The impacts of unrestricted resource consumption can be severe. It can cause a denial of service due to resource starvation and significantly increase operational costs, such as higher CPU demand, increased cloud storage needs, and infrastructure scaling. An API is vulnerable if it lacks appropriate limits or if the limits are set too low or too high. Examples of critical limits include execution timeouts, maximum memory allocation, maximum number of file descriptors, processes, and upload file size. Let's look at an example of unrestricted resource consumption. Imagine an API with no rate limiting, leading to an excessive number of requests. This can cause server overload, degrading service quality for other users, and significantly increasing operational costs. To identify resource consumption vulnerabilities, test your API endpoints by sending multiple concurrent requests and analyze the responses. Look for signs of weakness in how the API manages and limits resource use. Preventing unrestricted resource consumption involves implementing limits on how often a client can call the API within a specified time frame. Notify clients when these limits are exceeded and provide reset information. Additionally, add server-side validation for query parameters and request bodies to control the number of records returned. Let's go to the next risk from the list. Let's speak about broken function level authorization, or BFLA, which is number 5 on the list. Today we will explore this vulnerability and discuss strategies to safeguard your APIs from unauthorized function access. BFLA, or broken function level authorization, occurs when API functions lack proper access controls, allowing unauthorized users to perform actions they shouldn't. While BOLA focuses on data access, BFLA is about the ability to alter or delete data. Attackers exploit BFLA by sending legitimate API calls to endpoints they shouldn't have access to. These calls can be made by anonymous users or users with lower privileges, making it easy to exploit exposed endpoints. Authorization checks for functions are often misconfigured because of complex user roles and hierarchies. APIs are usually structured, which makes it easier for attackers to discover and exploit these authorization flaws. The impacts of BFLA can be severe, leading to unauthorized access to critical functions, especially administrative ones. This can result in data disclosure, data loss, data corruption, and even service disruption. Consider a fintech API that allows attackers to transfer funds from other users' accounts. For example, if an attacker can access an administrative endpoint intended for transferring funds, they can perform unauthorized actions. Let's look at a sample request. In this example, the attacker uses the post/admin/transfer endpoint to transfer funds from the victim's account to their own. If the API lacks proper authorization checks, this request would be processed, leading to unauthorized fund transfers. To identify BFLA vulnerabilities, test your API endpoints by sending requests from users with different privilege levels. Look for any functionality that can be accessed or altered without proper authorization checks. Preventing BFLA involves implementing a consistent and comprehensive authorization module. Ensure that all access is denied by default and explicitly granted to specific roles. Review your API endpoints against function-level authorization flaws, considering the application's business logic and group hierarchy. Time to speak about the next risk from the list. Let's speak about unrestricted access to sensitive business flows, which is number 6 on the list. Unrestricted access to sensitive business flows happens when attackers identify and exploit API-driven workflows. This can lead to attackers obstructing other users by spamming them, depleting the stock of highly sought-after items, or disrupting expected application functionality. Attackers start by understanding the business model supported by the API. They identify sensitive business flows and automate access to these flows, causing harm. This could involve spamming users, draining product stock, or disrupting services. A lack of a holistic view of the API and business requirements often contributes to this vulnerability. Attackers manually identify and exploit the resources involved in the target workflow, understanding how they work together to bypass existing mitigation mechanisms. The primary impact of unrestricted access to sensitive business flows is business-related rather than technical. For example, exploitation might prevent legitimate users from purchasing a product or disrupt the internal economy of a game. Let's consider an example where an attacker automates access to a reservation system to book all available slots. By automating API requests, the attacker can block legitimate users from making reservations. Let's examine a sample request. In this example, the attacker automates the post/reserve request to book all available slots for a specific date and time. If the API lacks proper controls, these automated requests can quickly fill up all the slots, preventing legitimate users from making reservations and demonstrating the importance of implementing robust protective measures. To identify vulnerabilities in business flows, test your API-driven workflows to pinpoint potential misuse. Look for patterns of automated access that could signal exploitation attempts, such as rapid successive requests or unusual usage patterns. Preventing unrestricted access requires a dual approach. From a business perspective, identify critical workflows that could be exploited. From an engineering standpoint, implement protection mechanisms to mitigate these risks. Let's explore some effective methods. Effective protection mechanisms include device fingerprinting to deny service to unexpected client devices, human detection using CAPTCHA or advanced biometric solutions, analyzing user flows to detect non-human behavior patterns, blocking IP addresses from Tor exit nodes and known proxies, securing and limiting access to machine-to-machine APIs, such as developer and B2B APIs. All right, next risk from the list. Time to speak about server-side request forgery, or SSRF, which is number 7 on the list. Today, we will explore this vulnerability and discuss how to protect your APIs from unauthorized requests. Server-side request forgery, or SSRF, occurs when an attacker can control the remote resources retrieved by an application. By supplying specific URLs, attackers can access private data, scan internal networks, or even execute remote code. Attackers exploit SSRF by finding API endpoints that access a URI provided by the client. Basic SSRF, where the response is returned to the attacker, is easier to exploit than blind SSRF, where the attacker does not receive feedback on the success of the attack. Modern application development often encourages accessing URIs provided by clients. A common weakness is the lack of or improper validation of these URIs, which can be exploited by attackers. Successful SSRF attacks can lead to internal service enumeration, information disclosure, and bypassing of firewalls. In severe cases, SSRF can cause denial of service or use the server as a proxy for malicious activities. Let's consider an example where an attacker manipulates an API request to access internal resources. This example demonstrates how an attacker can retrieve sensitive data from the server. In this example, the attacker manipulates the resource URL parameter in the request body to point to an internal resource. If the API does not properly validate this input, the server will retrieve and return the sensitive data from the internal resource, illustrating the SSRF vulnerability. To identify SSRF vulnerabilities, inspect API endpoints that access user-provided URIs. Test for both basic and blind SSRF by analyzing API responses and observing server behavior. Preventing SSRF involves isolating resource fetching mechanisms to prevent access to internal resources. Use allow lists for remote origins, URL schemes, ports, and media types to control which resources can be accessed. Additional protection techniques include disabling HTTP redirections, using well-tested URL parsers, validating and sanitizing all client-supplied input data, and avoiding sending raw responses to clients. All right, let's go to the next risk from the list. Let's speak about security misconfiguration, which is number 8 on the list. Today, we will explore this wide-ranging vulnerability and discuss strategies to safeguard your API infrastructure. Security misconfiguration refers to a range of vulnerabilities within the systems that host APIs. These flaws can undermine the confidentiality, integrity, and availability of an API provider's data, leading to severe security breaches. Attackers exploit security misconfigurations by searching for unpatched vulnerabilities, common endpoints, and unprotected files or directories. These weaknesses can provide unauthorized access or reveal critical system details. Security misconfigurations can happen at any level of the API stack, from network settings to application configurations. Automated tools are available to detect and exploit these issues, identifying unnecessary services or outdated options. The impacts of security misconfigurations can be severe. Exposure of sensitive data and system details can lead to full server compromise, resulting in data breaches and unauthorized access to critical systems. Let's consider an example where an API endpoint allows file uploads without proper validation. An attacker could exploit this misconfiguration by uploading a malicious script, which could then be executed on the server. Let's examine a sample request. In this example, the attacker uploads a file named maliciousScript.sh to the API endpoint. If the API does not validate the file type and content properly, this script could be executed, potentially giving the attacker control over the server. To identify security misconfigurations, use automated tools to scan for issues in headers, cookies, and SSL settings. Additionally, manually inspect configurations to identify inconsistencies and potential vulnerabilities. Preventing security misconfigurations involves implementing a hardening process to ensure secure and consistent deployments. Regularly review and update configurations across the API stack, including orchestration files, API components, and cloud services. Additional protection techniques include ensuring encrypted communication, TLS, for all API interactions, restricting HTTP methods to those necessary for API functionality, and implementing cross-origin resource sharing and security headers for web-based APIs. Onwards to the next risk from the list. Time to speak about improper inventory management, which is number 9 on the list. Today we will explore this vulnerability and discuss strategies to secure your API versioning and inventory. Improper inventory management refers to the exposure of non-production and outdated API versions. These versions often lack the rigorous security measures applied to production APIs, making them vulnerable to attacks. Attackers exploit improper inventory management by targeting old API versions or unpatched endpoints with weaker security. This can lead to unauthorized access to sensitive data or the ability to perform unauthorized actions. Outdated documentation makes it difficult to identify and fix vulnerabilities. The lack of proper inventory and decommissioning strategies results in unpatched systems, which are prone to attacks. The impacts of improper inventory management can be severe. Attackers may gain access to sensitive data or even take control of servers. Deprecated endpoints might expose administrative functions or known vulnerabilities. Let's consider an example where an outdated API endpoint remains accessible, exposing sensitive data. This demonstrates how attackers can exploit old versions to access critical information. In this example, an attacker accesses an old API endpoint API v1 users using an outdated token. If this endpoint is still functional and lacks updated security measures, it can expose sensitive user data, highlighting the importance of proper inventory management. To identify inventory management vulnerabilities, use outdated API documentation and changelogs to find unsupported endpoints. Test for vulnerabilities by making requests to old versions and non-production APIs to see if they are still accessible. Preventing improper inventory management involves maintaining a comprehensive inventory of all API hosts and their environments. Regularly update and decommission outdated or non-production API versions to ensure they are not vulnerable to attacks. Additional protection techniques include implementing API security firewalls for all exposed versions, not just the production ones. Avoid using production data in non-production APIs unless they are secured to the same level as the production environment. Onwards to the next and also the last risk from the list. Let's speak about unsafe consumption of APIs, which is number 10 on the list. Today, we'll explore this unique vulnerability and discuss strategies to secure data from third-party APIs. Unsafe consumption of APIs focuses on the risks faced by API consumers. It's primarily a trust issue, meaning that data from third-party APIs should be treated as untrusted, similar to how we handle user input. Attackers exploit unsafe API consumption by targeting and compromising third-party APIs integrated with the target application. Once compromised, these third-party APIs can become new attack vectors, potentially compromising the consumer system. Developers frequently trust external APIs without proper verification, relying on weaker security practices like inadequate transport security, authentication, and input validation. This can open the door to various attacks. The impact of unsafe API consumption varies depending on how the application uses the data. Potential consequences include exposure of sensitive information, various injection attacks, and even denial of service. Let's consider an example where a weather application integrates data from a third-party weather API. If this third-party API is compromised, malicious data could be sent to the weather app, potentially leading to a security breach. Let's examine a sample request. In this example, the weather app sends a request to the third-party weather API. If the response contains malicious data, it could exploit vulnerabilities in the weather app, demonstrating the importance of treating third-party API data as untrusted. To identify unsafe API consumption, assess the security posture of third-party APIs before integration. Regularly review and test data received from these APIs to ensure it meets security standards. Preventing unsafe API consumption involves evaluating service providers for their API security measures, ensuring secure communication channels, TLS, for all API interactions, and always validating and sanitizing data received from third-party APIs. Additional protection techniques include maintaining an allow list for known and trusted API endpoints and avoiding blindly following redirects from third-party APIs. All right, let's do some labs and have a more hands-on approach. I'll demonstrate you through multiple labs how some of these API vulnerabilities work in action. All right, now I'll be demonstrating how to find exposed API documentation and use it to delete a user account. We'll explore the lab scenario, understand how API documentation can be leveraged by attackers, and finally, solve the lab by leveraging the exposed API documentation. Let's get started. API documentation provides details about the available endpoints, methods, parameters, and responses of an API. It is essential for developers to understand how to interact with the API effectively. However, if exposed publicly or insufficiently secured, this documentation can be a valuable resource for attackers to discover and exploit vulnerabilities. API documentation is useful to attackers because it helps them identify endpoints and methods that can be exploited, understand the parameters and data required for requests, discover hidden or undocumented endpoints that may contain vulnerabilities. By leveraging this information, attackers can craft specific requests to exploit the API. To discover API documentation, attackers can inspect API responses and endpoints for references to documentation, use directory brute forcing techniques to find hidden documentation files or directories, analyze application behavior to uncover any references to documentation URLs. Once the documentation is found, it can provide a roadmap for exploiting the API. Alright, time for the hands-on part. Let's now demonstrate how to solve this lab by finding and exploiting the exposed API documentation to delete the user Carlos. In Burp's browser, log into the application using the credentials username Wiener and password Peter. Update your email address to generate relevant requests that we can inspect. In proxy, then HTTP history, right-click the patch/API/user/Wiener request and select Send a Repeater. Go to the Repeater tab, send the patch/API/user/Wiener request. Notice that this retrieves username and email information for the user Wiener. This step helps us understand the structure and response of the request, which will be useful for further exploitation. Remove /Wiener from the path of the request so the endpoint is now /API/user, then send the request. Notice that this returns an error because there is no user identifier. This step helps us identify the potential for discovering more information by altering the endpoint path. Remove /user from the path of the request so the endpoint is now /API, then send the request. Notice that this retrieves API documentation. Discovering the API documentation endpoint reveals detailed information about the available API methods, which can be used for further exploitation. Right-click the response and select Show Response in Browser. Copy the URL. Paste the URL into Burp's browser to access the documentation. Notice that the documentation is interactive. Accessing the documentation in a browser provides a more user-friendly interface to interact with the API. To delete Carlos and solve the lab, click on the Delete row, enter Carlos, then click Send Request. Now, the lab is solved. Let's speak about how to remediate this issue. To secure API documentation and prevent exploitation, you should restrict access to API documentation, ensure that only authorized users can view and interact with the documentation, implement proper authentication and authorization, verify that users have the necessary permissions before allowing them to perform actions. Regularly audit and monitor API usage. Continuously monitor API activity to detect and respond to any suspicious behavior. By implementing these security measures, you can protect your API from being exploited through its documentation. To summarize, we've successfully exploited an API endpoint using exposed documentation to delete a user account. We've also discussed how to remediate this vulnerability by securing API documentation, implementing authentication and authorization, and monitoring API usage. Understanding and securing API endpoints and documentation is crucial for maintaining the integrity and security of your web applications. Let's move on to the next lab. Let's exploit server-side parameter pollution in a query string. More precisely, I'll be demonstrating how to log in as the administrator and delete a user account by exploiting server-side parameter pollution. We'll explore the lab scenario, understand how parameter pollution works, and finally, solve the lab by leveraging the discovered vulnerabilities. Let's get started. Server-side parameter pollution occurs when an application processes multiple instances of a parameter from a single request. This can lead to unintended behavior and vulnerabilities such as unauthorized access or data manipulation. By understanding how parameters are processed, attackers can craft malicious requests to exploit these vulnerabilities. In URL query syntax, parameters are passed using the query string, which starts after the question mark in the URL. Each parameter is separated by an ampersand and includes key value pairs. Understanding this syntax is crucial for crafting requests to exploit server-side parameter pollution. Error messages can be very informative, providing insights into how the server processes requests. By analyzing these messages, attackers can infer the structure and behavior of the API, which helps in crafting requests that exploit vulnerabilities such as server-side parameter pollution. Let's now demonstrate how to solve this lab by exploiting server-side parameter pollution to log in as the administrator and delete the user Carlos. In Burp's browser, trigger a password reset for the administrator user. In Burp, go to Proxy, then HTTP History. Notice the post/forgot password request. Right-click the post/forgot password request and select Send to Repeater. And the related /static/js/forgot password.js JavaScript file. As we can see, the JavaScript file contains code that showcases an additional parameter that is needed to properly reset the password. We can manipulate this in further steps. In the Repeater tab, resend the request to confirm that the response is consistent. Change the value of the username parameter from administrator to an invalid username, such as administrator X. Send the request. Notice that this results in an invalid username error message. This helps us understand how the server validates the username parameter and handles errors. Attempt to add a second parameter value pair to the server-side request using a URL encoded ampersand character. For example, add URL encoded ampersand x =, y. Send the request. Notice that this returns a parameter is not supported error message. This suggests that the internal API may have interpreted ampersand x =, y as a separate parameter instead of part of the username. Attempt to truncate the server-side query string using a URL encoded hash character which equals to %23. Send the request. Notice that this returns a field not specified error message. This suggests that the server-side query may include an additional parameter called field, which has been removed by the hash character. Add a field parameter with an invalid value to the request. Truncate the query string after the added parameter value pair. For example, add URL encoded ampersand field =, x hash. Send the request. Notice that this results in an invalid field error message. This suggests that the server-side application may recognize the injected field parameter. Right-click the post/forgot password request and select Send to Intruder. In the Intruder tab, add a payload position to the value of the field parameter as shown on the screen. Go to the Payloads tab, click Add from List. Select the built-in server-side variable name's payload list, then start the attack. Review the results. Notice that the requests with the username and email payloads both return a 200 response. Brute forcing the field parameter helps identify valid field names that can be used in the request. Send the request to the Repeater tab. Then send the request. Notice that this returns the original response. In Proxy, then HTTP History, review the /static/js/forgot password.js JavaScript file. Notice the password reset endpoint, which refers to the reset_token parameter. In the Repeater tab, change the value of the field parameter from email to reset_token. Send the request. Notice that this returns a password reset token. Make a note of this. By using the valid field name reset_token, we can retrieve the password reset token for the administrator account. In Burp's browser, enter the password reset endpoint in the address bar. Add your password reset token as the value of the reset_token parameter as shown on the screen. Set a new password. Log in as the administrator user using your new password. Resetting the password allows us to log in as the administrator and perform administrative actions. Go to the admin panel and delete Carlos to solve the lab. Great. Let's now speak a bit about remediation. To prevent exploitation of server-side parameter pollution, you should validate and sanitize all input parameters. Ensure that only expected parameters are processed by the server. Implement proper error handling and messaging. Avoid exposing internal details through error messages. Regularly audit and monitor API endpoints. Continuously monitor API activity to detect and respond to any suspicious behavior. By implementing these security measures, you can protect your API from being exploited through parameter pollution. To summarize, we've successfully exploited server-side parameter pollution to log in as the administrator and delete a user account. We've also discussed how to remediate this vulnerability by validating input parameters, implementing proper error handling, and monitoring API endpoints. Understanding and securing API endpoints is crucial for maintaining the integrity and security of your web applications. Onwards to the next lab. Time to demonstrate how to exploit a hidden API endpoint to buy a product at a manipulated price. We'll explore the lab scenario, understand how to leverage HTTP methods and error messages, and finally solve the lab by purchasing a product at a price of $0. Let's get started. Unused API endpoints are endpoints that exist within the API but are not actively used or documented. These endpoints might have been left over from previous versions or development stages. Although not intended for use, they may still be accessible and exploitable if discovered, providing attackers with an opportunity to manipulate the application's behavior. RESTful APIs use different HTTP methods to perform various actions on resources. Common HTTP methods include GET, POST, PUT, DELETE, and PATCH. By changing the HTTP method of a request, you can potentially reveal additional functionalities or behaviors of the API that are not immediately obvious. This technique is useful for discovering hidden or unused endpoints. Error messages can provide valuable information about the API's expected input. By analyzing these messages, you can gain insights into the required parameters, data formats, and conditions needed to construct valid requests. This information is crucial when attempting to exploit hidden or unused API endpoints. Let's now demonstrate how to solve this lab by finding and exploiting a hidden API endpoint to buy the lightweight leather jacket at a price of $0. In Burp's browser, access the lab and click on a product. In Burp proxy, then HTTP history, notice the API request for the product, such as /API/products/1/price. Right-click the API request and select Send to Repeater. In the Repeater tab, change the HTTP method for the API request from GET to Option. Notice that the response specifies that the GET and PATCH methods are allowed. The Options method reveals the allowed methods for the endpoint, indicating that PATCH can be used to modify the resource. Change the method for the API request from GET to PATCH, then send the request. Notice that you receive an unauthorized message. This indicates that authentication is required to use the PATCH method. In Burp's browser, log into the application using the credentials Wiener and Peter. Click on the lightweight leather jacket product. In Burp proxy, then HTTP history, right-click the /API/products/1/price request for the leather jacket and select Send to Repeater. In the Repeater tab, change the method for the API request from GET to PATCH, then send the request. Notice that this causes an error due to an incorrect content type. The error message specifies that the content type should be application JSON. The error message indicates the need to set the correct content type header and format the request body as JSON. Add a content type header and set the value to application/JSON. Add an empty JSON object as the request body, then send the request. Notice that this causes an error due to the request body missing a price parameter. The error message provides information about the required parameters. Add a price parameter with a value of 0 to the JSON object. Send the request. In Burp's browser, reload the leather jacket product page. Notice that the price of the leather jacket is now $0. By setting the price to 0, we have manipulated the price of the product. Add the leather jacket to your basket. Go to your basket and click Place Order to solve the lab. The purchase completes at the manipulated price, demonstrating the exploitation of the hidden API endpoint. Let's speak about remediation. To secure API endpoints and prevent exploitation, remove or secure unused endpoints. Ensure that endpoints not intended for use are properly secured or removed. Implement proper authentication and authorization. Verify that only authorized users can access and modify resources. Regularly audit and monitor API endpoints. Continuously monitor API activity to detect and respond to any suspicious behavior. By implementing these security measures, you can protect your API from being exploited through hidden or unused endpoints. To summarize, we've successfully exploited a hidden API endpoint to manipulate the price of a product and purchase it for $0. We've also discussed how to remediate this vulnerability by securing API endpoints, implementing authentication and authorization, and monitoring API activity. Understanding and securing API endpoints is crucial for maintaining the integrity and security of your web applications. Let's go to the next lab. Let's demonstrate how to exploit a mass assignment vulnerability to buy a product at a manipulated discount. We'll explore the lab scenario, understand how mass assignment vulnerabilities work, and finally solve the lab by leveraging the discovered vulnerability. Let's get started. Mass assignment is a feature in many web frameworks that allows setting multiple attributes of an object at once, typically by passing a hash of attribute names and values. While convenient for developers, this can lead to unintended behavior if not properly secured, allowing attackers to modify attributes that should not be exposed. Hidden parameters are those that exist in the back end but are not exposed to the front end. These parameters may be used by the application internally, but can be manipulated by attackers if they are not properly secured. Identifying and exploiting these hidden parameters is a common technique in mass assignment attacks. To identify mass assignment vulnerabilities, inspect API requests and responses for discrepancies. Look for parameters and responses that are not present in requests, as these may be hidden parameters that can be manipulated. Understanding the application's data flow and structure is crucial for identifying potential vulnerabilities. To exploit mass assignment vulnerabilities, add hidden parameters to your requests and modify their values to manipulate the application's behavior. By doing so, you can achieve unauthorized actions such as applying discounts, changing user roles, or bypassing security checks. Let's now demonstrate how to solve this lab by exploiting a mass assignment vulnerability to buy the lightweight Elite leather jacket at a manipulated discount. In Burp's browser, log into the application using the credentials Wiener and Peter. Click on the lightweight Elite leather jacket product and add it to your basket. Go to your basket and click Place Order. Notice that you don't have enough credit for the purchase. This indicates that we need to find a way to adjust the price or apply a discount to complete the purchase. In proxy, then HTTP history. Notice both the GET and POST API requests for /API/checkout. Notice that the response to the GET request contains the same JSON structure as the POST request. Observe that the JSON structure in the GET response includes a chosen _discount parameter, which is not present in the POST request. The chosen _discount parameter in the GET response, but not in the POST request, suggests a hidden parameter that we can potentially exploit. Right-click the POST /API/checkout request and select Send to Repeater. In Repeater, add the chosen _discount parameter to the request. The JSON should look like what's shown on the screen. Send the request. Notice that adding the chosen _discount parameter doesn't cause an error. This indicates that the parameter is recognized and accepted by the server. Change the chosen _discount value to the string on the screen, then send the request. Observe that this results in an error message as the parameter value isn't a number. This suggests that the server is processing the chosen _discount parameter and expects a numerical value. Change the chosen _discount percentage to 100, then send the request. Go to the Burp browser, reload the My Cart page. Notice that the total price is now $0 and that our order is on the way. Also, the lab is solved. By setting the discount to 100%, we have manipulated the price to $0, allowing us to purchase the product. Let's now speak about remediation. To prevent mass assignment vulnerabilities, you should use strong parameter filtering and whitelisting. Ensure that only intended parameters can be set through mass assignment. Implement proper validation and authorization checks. Verify that users have the necessary permissions to modify specific attributes. Regularly audit and monitor API endpoints. Continuously monitor API activity to detect and respond to any suspicious behavior. By implementing these security measures, you can protect your API from being exploited through mass assignment. To summarize, we've successfully exploited a mass assignment vulnerability to manipulate the price of a product and purchase it for $0. We've also discussed how to remediate this vulnerability by implementing parameter filtering, validation, and monitoring. Understanding and securing API endpoints is crucial for maintaining the integrity and security of your web applications. On to the next, and at the same time, the last lab. Let's see how to exploit server-side parameter pollution in a REST URL. Today I'll be demonstrating how to log in as the administrator and delete a user account by exploiting server-side parameter pollution. We'll explore the lab scenario, understand how parameter pollution works, and finally solve the lab by leveraging the discovered vulnerabilities. Let's get started. Server-side parameter pollution occurs when unsanitized user input is included in the URL path or query string of a server-side request. This can lead to unintended behavior and vulnerabilities such as unauthorized access or data manipulation. By understanding how parameters are processed, attackers can craft malicious requests to exploit these vulnerabilities. Path traversal sequences like .. can be used to navigate to different directories in the file system, potentially accessing restricted areas. The query string starts after the question mark character in a URL and contains key value pairs separated by ampersand. Understanding these concepts is crucial for crafting requests to exploit server-side parameter pollution. Error messages can provide valuable information about how the server processes requests. By analyzing these messages, you can gain insights into the required parameters, data formats, and conditions needed to construct valid requests. This information is crucial when attempting to exploit server-side parameter pollution vulnerabilities. To discover API documentation, inspect API responses and paths for any references to documentation. You can also use directory traversal and brute forcing techniques to find hidden documentation files or directories. API documentation provides a roadmap for understanding the API's structure and endpoints, which can be valuable for exploitation. Let's now demonstrate how to solve this lab by exploiting server-side parameter pollution to log in as the administrator and delete the user Carlos. In Burp's browser, trigger a password reset for the administrator user. In proxy, then HTTP history, notice the post/forgot password request and the related /static/js/forgot password.js JavaScript file. Right-click the post/forgot password request and select Send to Repeater. In the Repeater tab, resend the request to confirm that the response is consistent. Submit URL encoded administrator hash as the value of the username parameter. Notice that this returns an invalid root error message, suggesting that the server may have placed the input in the path of a server-side request, and the fragment has truncated some trailing data. This suggests that the input is being used in the URL path, and the fragment character hash is causing truncation. Change the value of the username parameter from administrator %23 to URL encoded administrator ? Then send the request. Notice that this also returns an invalid root error message, suggesting that the input may be placed in a URL path as the ? Character indicates the start of the query string. This indicates that the server is placing the input in the URL path, and the ? Character is affecting the URL structure. Change the value of the username parameter to /administrator, then send the request. Notice that this returns the original response, suggesting that the request accessed the same URL path as the original request. This indicates that the input is being placed in the URL path, and the / sequence is being interpreted as the current directory. Change the value of the username parameter from /administrator to /administrator, then send the request. Notice that this returns an invalid route error message suggesting that the request accessed an invalid URL path. This indicates that the server is processing the .. sequence to navigate to a different directory. Change the value of the username parameter from .. administrator to .. %23. Notice the invalid route response. At this level, add some common API definition file names to the URL path. For example, submit the following payload shown on the screen. Notice that this returns an error message containing the following API endpoint for finding users: /API/internal /v1/user/username/field/field. This provides the structure of an internal API endpoint, which can be used for further exploitation. Update the value of the username parameter using the structure of the identified endpoint. Add an invalid value for the field parameter. Follow instructions on the screen. Send the request. Notice that this returns an error message because the API only supports the email field. Add email as the value of the field parameter as shown on the screen. Send the request. Notice that this returns the original response, suggesting that the server recognizes the injected field parameter and that email is a valid field type. In proxy, then HTTP history, review the /static/js/forgotpassword.js JavaScript file. Identify the password reset endpoint, which refers to the password reset token parameter. In the repeater tab, change the value of the field parameter from email to password reset token. Send the request. Notice that this returns an error message because the password reset token parameter is not supported by the current version of the API. Using the /API/endpoint identified earlier, change the version of the API and the value of the username parameter payload as shown on the screen. Send the request. Notice that this returns a password reset token. Make a note of this. By changing the API version, we can access the endpoint that supports the password reset token parameter. In Burp's browser, enter the password reset endpoint in the address bar. Add your password reset token as the value of the password reset token parameter, as shown on the screen. Set a new password. Log in as the administrator using your new password. Go to the admin panel and delete Carlos to solve the lab. Voila! The lab is solved. Time to speak about remediation. To prevent exploitation of server-side parameter pollution, you should validate and sanitize all input parameters. Ensure that only expected parameters are processed by the server. Implement proper error handling and messaging. Avoid exposing internal details through error messages. Regularly audit and monitor API endpoints. Continuously monitor API activity to detect and respond to any suspicious behavior. By implementing these security measures, you can protect your API from being exploited through parameter pollution. To summarize, we've successfully exploited server-side parameter pollution to log in as the administrator and delete a user account. We've also discussed how to remediate this vulnerability by validating input parameters, implementing proper error handling, and monitoring API endpoints. Understanding and securing API endpoints is crucial for maintaining the integrity and security of your web applications. Thank you for watching this video. Subscribe to learn more, drop a like to support the channel, and comment any questions you have.